Hello everyone. Today we're looking at another Leetcode problem. This is 2014, finding the longest subsequence repeated k times. Now for this problem we are given character string s of length n and another integer value k. With this we have to find the longest subsequence which repeats k times. Okay, let us look at an example and then understand this better. So let's take the example that they've given. Let's lead code. Okay, so the first thing is I need to find a subsequence. Okay, a subsequence is nothing but characters taken in the order in which it appears in original string, but not necessarily consecutive ones. So let's say I start from here, I pick this, and then from here, let's say I go here and I pick this. So I have created a subsequence that looks like this. Now, next part to this problem is that it must be repeated k10. Now, is LT repeating k times? K for this particular problem is given as 2. So this is definitely not repeating 2 times. So this is not a valid subsequence for this problem. I can now take another subsequence. Let's say I take ET. Okay. Now this particular subsequence is repeating 2 times. Okay, so this is a valid subsequence for this problem. But the problem has some additional constraint. The first one is that we need to find the longest subsequence. The second one is what they're saying is that they want us to find the largest lexicographically graphical subsequence. Okay, so let's explore a little bit more. Now let's try to generate a little longer subsequences. So I can generate LET and LET. Okay, so LET does repeat 2 times, so this is a yes. Another thing that we can do is ETE and ETE. So ETE is also repeating 2 times. So these are valid options for the first constraint, and using the second constraint of largest lexicographical subsequence, I will return this value. Okay, so this will be my answer. Alright, so as you might have seen with the example, generating this subsequence can get super exhausted, and then after generating the subsequence you have to validate that if it repeats k time, which is going to be order of n, scanning through the whole string again. So this is going to be a really large computation. So let's try to optimize this a little bit more. First, let's try by start by getting the character counters. Okay, so let's do that. We write a problem again. This time we're going to write the character code count. So L appears 2 times, E appears 4 times, T appears 2 times, S appears 1 time, L appears 2 times, E is 4, 4, 2, 1, 1, 1, 4. Okay, now as you might have seen in these earlier examples, I did not use COD, and that's because the counts are lesser than the repeat count that I have. And what that means is that using C, I can never generate generate a subsequence that repeats twice. Okay, cannot generate a subsequence that repeats k times. And so there's no point even considering these characters for our subsequent generation. So that's our first step, which is take your original string and then compress it to get valid characters which have frequency greater than or equal to k, so that I can generate k repeats. So now what this leaves us is 2 is greater than or equal to 2, 4 is greater than 2, 2 is equal to 2. So all of these will get picked up. L, E, T, S will not get picked up. L, E, E, T, E. So this is my new string. Now, using this new string, I need to find all of the subsequences that repeat k times, and of that I need to get the longest subsequence and the subsequence which is in lexicographical largest order. Okay, so given an input like this, because we also want lexicographically largest order, why don't we take the uniques from here? So let's say L, E, T, and then sort it in reverse order. So we get T, L, E, but I hope we don't. Jokes apart. So we get T, L, E here. And now the next step is to generate all possible subsequences and then validate if it exists in string S and if it exists k times. So instead of just checking if it exists in S, we want to check if it exists in S k times. Okay, so for our particular example, what we want to do is identify the longest subsequence which is lexicographically largest, and we want to make sure that there are 2 repeats of those. Okay, now using these characters I can keep generating as many strings as I want of as long as many digits as I want. Okay, so let us also really quickly talk about the constraints right now to understand how this is going to be okay. So what the constraints say is that my k is lesser than or equal to 2000. That means at max I might want my subsequence to repeat 2000 times. Another thing that they tell us is that n is lesser than k times 8, which means n by k is lesser than 8. Now, if this was entirely n, the string, and this has repeated k times, then what I'm getting is the length of this subsequence. So what now we are talking about is the length of subsequence will be lesser than 8, which means the max length will be equal to 7. Now, this is something that is not too much for us to consider. So, plus we are doing an optimization, so it should be okay in terms of the problem capacity. So, let's now think about given few characters, let's say X, Y, Z, how can I generate my subsequences? There are 2 ways of generating these subsequences. One is depth first search, which means you take the first character X and then you add X, Y, Z to it, and then you further add X, Y, Z to it. So here also X, Y, Z, here also X, Y, Z, and you keep doing this, okay, till some condition makes this the end condition. Okay, we'll talk about that. But this is the depth first approach. So you're covering the depth first. You're generating the longest possible subsequence. You're continuously generating the longest possible subsequence. Another approach is, let me write it here, which is a BFS. So you start with XYZ and this is a level order, which means you will generate all the subsequences of length 1, and then you will move to all the subsequences of length 2, and you will move to all the subsequences of length 3. So in this case, you'll pop the leftmost element from the queue, and then you again apply x, y, and z to it, and then you push it back to the queue. So now your queue will look like xx, xy, and xz. So first you're processing all the single digit subsequences. Next you'll start processing all possible double length or subsequences of length 2. Now this approach is preferred over this approach because at every level, okay, so let's say this is level 1, this is level 2, and so on, you are identifying the subsequences that are valid. Okay, you will identify the subsequences that are valid, and then only you will proceed. So what will happen is, by the time you come to the nth level, you will have the longest possible subsequence, which meets your criteria identified. So at this level, at third level, first you will identify the valid subsequence of length 3. At this level, you will identify the first subsequence of length 2, and so on. And so when you come to the level n, you will first identify the subsequence of the length n, valid subsequence of length n, before proceeding further. And so this is a good approach. Now, why is DFS not a good approach? Because what happens here is we are not focused on doing a comparison with all of the different levels. What we do is first we go down and we start generating the longest possible subsequence. Now, this longest possible subsequence that I've generated may not be the most valid one. So this ends up creating or generating all of the possibilities before I can even explore it. But the BFS is a very good option if you're looking to find a shortest distance or a longest distance or something like that. In this case, we are trying to find the longest subsequence that is valid. So we keep going, but we're going length by length. So that gives us an advantage here. Now, this said, we have identified the core elements of our problem. What are they? The first one is I need a compressed string. Okay, this only has characters that will help me to generate subsequences with k repeats. Okay, and the second thing is I am going to do a breadth first search to find level by level best subsequence. Okay, and the way the BFS is going to grow is that every time I create a new subsequence, I will verify this. I'll verify if it is a valid one, which means it should repeat k times. That's all I need to check, because this is going to be processing in the lexicographical order, because that's how I'm going to give my input to it. So the only thing that I need to then check is if the new subsequence generated does repeat k times. So now with these two elements already identified, let's look at the pseudocode which will bring all these concepts together. So the first thing that we do is in Python, from collections import counter. Now the counter is nothing but a function, a built-in function for Python developers that they can use to count the characters. Let's say you have ABC, it'll give me A of occurrence frequency 1, like this. Okay, so I get this value from the counter. So I'll take count, so let's also get the function. So I'll say longest subsequence, and for this I got the input, which was S string K, which was integer. Okay, so let's say we start with count, which is nothing but counter of S. Now I've gotten the counter. Let's next compress the S. Okay, and I also sort it at the same time. So sorted C for C comma V. So remember I showed you that my counter will return this. So the key is going to be the character and the value is going to be the frequency. So I'm going to collect all the C's in counts.items, for which I'm going to collect all the C's if their value was greater than or equal to K. And then finally I'm going to sort the C that will give me the lexicographical largest order. Oh, sorry, I forgot. I want to do it in the reverse order, otherwise I'll get ascending list. So once this is done, I now use my Q, which is going to be useful for the BFS. I create a copy of my compressed S. Also copy is something that I had to import from copy, import, copy. Okay, so you start with your maxed string. This is what you're going to return. So at every step of the execution, you're going to keep checking for max SS. Alright, so while Q has some elements, you take a subsequence, okay, from the Q. Now that you've taken a subsequence, check if this is longer than max. Okay, if len of SS is greater than len of max SS, then this new subsequence becomes the max SS. Alright, now for C in compressed S, what are we doing is that for all of that compressed sorted TLE that we have taken, if I got, let's say, LE, then I add all of these possibilities. So I'm creating a new variation, a new SS of length 3. Okay, and so the final result will be LET, LEL, LEE. Okay, and then we will next verify, and only the ones that are repeating K times will be added back to the BFS queue. Alright, so let's see. New SS is equal to SS plus C. Now I'm going to create, I'm going to write a little bit of a Pythonic code, but I will also explain what that means. Iter S is equal to iter of S. This is nothing but, you can think of this as a for loop yet to be executed. So this is an iter function. What this is going to do is this is ready to iterate through your S, because we have to check whether our subsequence exists K time in the original S, not in the compressed S. Okay, so it's ready to iterate through this string starting with its pointer at the 0th index. And now what we're going to say is that my status is equal to all. Just hold on for a second. I'm gonna explain this. C in iter of S for C in new SS times K. So now what this is saying is, let's say if I had LWE. Okay, so my new SS is LWE. Now multiply that 2 times. I am looking for LWE. Okay, so for C in this, so first C is here. Okay, and this is looking here. This is probably not L, so you'll keep moving till you find L with this matches. So this moves forward, and then this pointer moves forward till this matches, and so on. And for all, it's saying if the match was 100%, then we will get a true status. So if we were able to exhaust this and find that in my S, we will get a true. So if status, then we're good. This is a valid subsequence of length 3 that we identified. Let's add it back. And finally, we return max of SS. So when does this execution stop? Because there is a while loop, and when does the queue really get exhausted? So the queue gets exhausted when I've probably, let's say if this was a subsequence, right? And let's say it was of length 2, and so I was able to verify and get that. Now, as I am continuously, so I got this, and then I expanded this. Expanded this to 3-character subsequence. Now, as I'm doing this, I'm expanding this, and then I might not find this in S. So this one does not get included. So as my subsequence length becomes bigger, I'm not going to find those occurrences in S, and not 2 times for sure. And so it's going to start exhausting whatever the queue I had. And by that time, I have already verified all the subsequence, and I have made sure that I have collected the largest subsequence in my variable max SS. So this is the logic. Now let's also look at the time complexity. Now we know that our our subsequence length is going to be n by k, which is lesser than 8. So we will have m dashes or n by k dashes, which is at max going to be 7. And now for each of these, I have a possibility of placing worst case 26 characters. So if I multiply all of these possibilities, this is 26 power n by k. And for each this is all of the subsequence that I can generate. And for each subsequence that I generate, I am doing this validation, which is order of n. So the total time complexity is 26 power n by k times n. Hope this made sense. For watching this video. I'll see you again with the next problem. Bye bye.